Hello everyone, this is Akshara of CSC AML A section. Today I am going to present this PPT for my AIT project on edge coloring of graphs with applications in coding. So this PPT is all about theoretical foundations and applications in coding, networking and error correction. So this is the slide 1. Slide 1 contains content. So this contains the topic we are going to cover in this PPT. Those are introduction, basics of graph coloring, Wiesen's theorem, examples of edge coloring algorithms, applications in computer science, applications in coding theory, edge coloring in network coding, edge coloring in scheduling, edge coloring error correction codes. So this is the slide 1. In this slide we are going to discuss about the introduction of edge coloring. So edge coloring. So edge coloring is the main topic in graph theory. So it's all about coloring the edges with different colors. So graph theory is a core area of discrete mathematics used in computer science, networking and coding. Edge coloring. So edge coloring means assigning colors to the edge so that no two edges incident on the same vertex share the same color. So this edge coloring helps in solving real world problems like scheduling, frequency, assignment and error detection. It plays a significant role in both theoretical and applied computer science. So in this slide we are going to discuss the basics of graph coloring. So basics of graph coloring, those include vertex coloring, edge coloring, chromatic index. So these are three main components in graph coloring. What is vertex coloring? Vertex coloring is nothing but assigning colors to the vertex. So in the below figure we can see there is a graph whose edges are same in color but vertices of different color. We can see no edge corresponding to the same vertex color. This graph is colored with three types of colors. Those are blue, green and red. So in vertex coloring, no two vertex can have same color with incident of same edge. Now let us discuss about edge coloring. Edge coloring is nothing but assigning colors to the edges. We can see the above figure there. It also required red, yellow, green and violet, three colors. But no vertex has same edge color. So this is one of the most important thing that a vertex coloring needs. Chromatic index. So chromatic index tells the minimum colors required for coloring a graph, whether it is vertex coloring or edge coloring. So we can see the definition. Minimum colors required to achieve a valid edge coloring is nothing but chromatic index. So xi represents chromatic index. Edge coloring reduces conflicts and ensures efficient use of resources. So now let's get into another slide. So this slide contains Wiesen's theorem. What is Wiesen's theorem? So fundamental results in edge colorings is nothing but Wiesen's theorem. So this theorem states for any simple graph, the chromatic index is del or del plus 1. So what is del? Del is nothing but the maximum degree of a vertex. If it is a complete graph of n vertices, then its highest degree is 5. So del represents degree of a graph, highest degree of a graph. For class 1 graphs, chromatic number is del. For class 2 graph, chromatic number is del plus 1. So this provides bounds to determine the number of colors required. So in this slide we are going to understand edge coloring with different types of graphs with their examples actually. So we have few graphs here. Those are bipartite, cyclic and complete graph. Here pictures related to them are also included. So now let's discuss about bipartite graph. So bipartite graph. Generally bipartite graph contain two sets of vertices, where each vertex in each set does not connect to the other vertex in the same set. It connects to the other vertex in the another set. So this is known as bipartite graph. So for chromatic number of bipartite graph is del. So we can see a picture of bipartite graph here. It has 4 vertices in one set and 4 vertices in another set. So these graph required 1, 2, so that is red, violet, green colors, 3 colors. It required at most 3 colors, and this is the least color for a bipartite graph. Cyclic graph. Cyclic graph means if a graph is in a cyclic structure, then it is known as cyclic graph. Even cycles needed 2 colors and odd cycles need 3 colors. So in the right side we can see a cycle graph. It has its vertices covered and edges are also covered. Vertices covered with the 3 colors, that is red, green and blue. Vertices are also covered with red, green, blue and yellow. So edge coloring need 4 colors and vertex coloring needed 3 colors. Complete graph. A graph is called complete graph if each vertex connected to the other every vertex. So that is known as complete graph. For chromatic index depends on partity of vertex. So below, on the right side below, we can see a complete graph where each vertex is connected to the every other vertex. So it needs n colors. If it is a n vertices, it needs n colors. If it is a 5 vertex graph, it needs 5 colors. So this is all about complete graph. Now let's get into other side containing edge coloring algorithm. So there are many algorithms used to color the edges, because you can see here picture here. It is very difficult to color a graph simply by identifying, because it is very complex. So we use some algorithms which makes the coloring is very easy. So some of the algorithms are greedy algorithm, matching based coloring, sequential and backtracking algorithm. Computational complexity increases with graph size. So now let us discuss about greedy algorithm. Assigns available colors sequentially and may not always be optimal. Matching based coloring decomposes graph into matchings. Sequential and backtracking algorithm used for exact coloring. So this is all about edge coloring algorithms. Now let's get into another slide. So this slide is all about applications in computer science. So what are the applications we are getting? Well, covering edges of a edges of a graph. So those applications are given here are 4. Now let us talk about them. Efficient resource allocation in system, register allocation in compilers to avoid variable conflicts, parallel processing means task distribution without conflicts, data communication, ensure no overlapping data paths. So these are few applications in computer science. Let's get into another slide. So now we are going to discuss about applications in coding theory. So what are the applications we are getting in coding theory? While coding actually, edge coloring also has applications in coding theory. So 4 are given here. Those are useful in designing error correction codes, ensures minimal interference in code transmission, important in data compression and network coding, reduces redundancy while maintaining accuracy of information. These are few applications in coding theory. So in this slide we are going to discuss about edge coloring in network coding. So what are edge coloring in network coding actually? So it nothing but network molded as graph with communication links as edges is called network coding. Edge coloring ensures parallel data transmission without interference. Increases throughput in high density networks. Like example, we can see assigning distinct frequencies to wireless channels is one of the example for edge coloring in network coding. Edge coloring and scheduling. What is edge coloring and scheduling? So it is mainly applied in timetabling and task scheduling. Edge, each edge represents a dependency between tasks. Edge coloring assigns time slots to avoid overlap. Crucial in communication systems where channel must be conflict free. So this is some information of edge coloring and scheduling. Yes. So this is one of the most important topic, that is edge coloring in error correction codes. So while coding on this edge coloring topic, we generally cause errors. So let us see some corrections to those error codes. Coding theory uses graph to model party check relationships. Edge coloring avoids repeated usage of same symbol in the neighborhood. Applied in LDPC codes means low density partiality check and turbo codes provides robust against data transmission errors. Study cases. Let us see some study cases on edge coloring. It is an example of channel assignment in wireless networks. Vertices represent devices, edges represent communication links. This is the basic thing in any system. Edge coloring ensures channels are allocated without interference, improves overall performance and reduces packet loss. So this is a case study while we when we observe few systems that is related to vertices coloring and edge coloring. So vertices represent devices and communication to those devices are nothing but edges. Challenges in edge coloring. Here are few challenges. Those are: edge coloring problem is NP complete in general graphs. Efficient algorithm exists for bipartite and special cases. Real networks require approximation algorithms. Dynamic graphs make coloring harder due to constant changes. Research directions. So here are some research directions. Those are: edge coloring in dynamic and evolving networks, integrated with quantum error correcting codes, development of hybrid algorithms combining heuristic and exact methods, applications in bioinformatics and cloud computing systems. Summary in this. So in this slide we are going to discuss what we have discussed before. So edge coloring is fundamental tool in graph theory. Wissner's theorem provides bounds for chromatic index. Essential applications in coding, scheduling, network and compilers. Ongoing research make it increasingly important in modern computing. Thank you. That's all for today's lecture.